Welcome to this module on FastAPI's concurrency model. By the end of this video, you will understand exactly how FastAPI can handle many simultaneous requests efficiently, what the event loop is doing behind the scenes, and how to write your route handlers so they work with the model instead of against it. Imagine a traditional web server. Every incoming request gets its own thread. That sounds fine at low traffic, but threads are not free. Each one consumes memory and competes for CPU scheduling time. Worse, most of what a web handler actually does is wait for a database query, wait for an external API, wait for a file read. A waiting thread is a blocked thread, and a blocked thread is wasted capacity. Under heavy load, you run out of threads before you run out of CPU. Think of a busy coffee shop with one experienced barista. They do not stand frozen, staring at the espresso machine, waiting for it to finish. They start the machine, then immediately turn and take the next order. When the machine beeps, they come back and complete the first drink. That is exactly what an async event loop does. It starts an I/O operation, hands control to the next task, and comes back when the result is ready. FastAPI is built on top of Starlet and uses Python's Async event loop. The event loop is a single loop running in a single thread that manages many coroutines at once. A coroutine is just an async def function, a function that knows how to pause itself. The await keyword is the pause point. It tells the event loop, I'm waiting on something slow, go do something else. When your function is a plain def instead of async def, FastAPI automatically offloads it to a threadpool, so it cannot accidentally block the loop. Let us walk through both handlers. The first route at app.get/weather/city is declared with async def. Inside, we open an HTTPX async client and call await on client.get. That await is the yield point. While the HTTP request to the weather service is in flight, the event loop is free to serve other incoming requests. When the response arrives, execution resumes right after the await. The second route, Fibonacci, is a plain def. It does pure CPU computation with no I/O to wait on. Because it is a regular function, FastAPI automatically runs it in a threadpool worker, keeping the event loop unblocked. When a request comes in, the event loop wraps your async def handler into a task and starts running it. The moment your code hits an await, say, awaiting a database query, the loop suspends that task and picks up another one that is already ready to continue. No thread switch, no OS scheduling overhead. Once the database responds, the original task is put back in the ready queue and resumes from exactly where it paused. The consequence is that one process can genuinely interleave hundreds of in-flight requests with very little overhead. The decision rule is straightforward. Use async def when your handler spends time waiting on something outside your process, a database, an API, a file. In those cases, a waiting lets the event loop serve other requests during that wait. Use a plain def when your work is CPU intensive or when you are using a library that has no async support. Calling a blocking function inside async def without await is the classic mistake. It freezes the entire event loop and kills your concurrency gains. To summarize, FastAPI uses a single event loop that cooperatively switches between coroutines whenever they hit an await. This gives you high concurrency without the cost of many threads. The rule to memorize is async def for anything that waits on I/O, plain def for anything that is CPU bound or uses a synchronous library. And if you take nothing else away, remember this: a blocking call inside async def is silent and deadly. It stalls every other request in the process.